Hi, everybody. Very excited today to talk to you about how we can use AI to transform the foundations of practical computing. So, So we live in an increasingly digital society where we have more apps, more systems, more screens. We also now have the wave of generative AI, so people are training models, and all of this is creating an increase in demand for compute and therefore energy usage. Now, all of these apps, systems, models that are being trained are sending requests to lots of different types of data centers from many different types of companies, like the one seen on the left, where data centers can range from thousands to tens of thousands to maybe even hundreds of thousands of machines, all processing this information simultaneously. Now, the response from these machines will then go to our consumer devices, for example, where we're running software, like the code seen on the right. Both the machines and the data centers, the consumer devices are all running software. And underlying all of this is the hardware that ensures that everything's running and running efficiently. Now, chips are starting to approach their fundamental physical limits, and Moore's law is coming to an end. And we need to find new and innovative ways to optimize the computing stack. So we thought, let's start with the code. So we asked ourselves, what if we could automatically optimize the world's code using reinforcement learning, discovering faster and innovative algorithms along the way that we hope could benefit both practitioners in what they implement and researchers in how they approach developing algorithms. But in order to do this, we wanted to start with what code do we want to even do this in? And if we look at how most developers program, most of them will be programming in higher-level languages like C++. Then a compiler takes this higher-level language and compiles it down to a lower-level language called assembly, which is much closer to the CPU and interacts with memory and registers. And assembly is executed line by line. An assembler then takes this code and then turns it into machine code that can be executed on a machine. So we decided by starting to see, can we generate algorithms from scratch in assembly? And we believed that there were optimizations and discoveries that could be made in this language because it was more flexible and lower level than what we might find in higher level languages, such as C++. But in order to do this, we wanted to figure out what were fundamental algorithms that we could tackle first. So we're going to build these algorithms in assembly, but what is a fundamental algorithm that is called trillions of times every day and really underlies everything that we do in many of the applications that we use? And for this, we decided to start with sorting algorithms. Now, sorting dates back many centuries. You can take it back to the great Library of Alexandria, where scholars were sorting different books in the library. Then fast forward to the 1890s, where tabulation machines were counting and sorting votes. Today, sorting is found all over in all the different types of applications we use, from retrieving information and prioritizing what we see, to determining what jobs to schedule and prioritizing their ordering, to displaying information, as well as ranking the search results that you would see when using recommendation systems. We even see sorting algorithms as being very prevalent in string processing. So now that we knew that we wanted to build algorithms from scratch in assembly, and specifically sorting algorithms, how do we get a reinforcement learning system to do so? So what we do is we devise a game, and we call this the assembly game. Now, the way this works is there's a player in the game. The player here is our system, AlphaDev. Now, the goal of the game is for AlphaDev to find a sorting algorithm that is both correct and fast, ideally faster than the state of the art. Now, the way this works, if you look at figure A, is AlphaDev takes in the state, which comprises the algorithm that it's currently building, as well as the state of memory and registers on the CPU. It then plays a move in this game, which is choosing an assembly instruction to add to the algorithm that it's building. Now, we have to reward or penalize AlphaDev for adding this instruction. So what we do is then we check the correctness and speed of the algorithm. For correctness, what we do in the case of sorting is you feed in a set of unsorted sequences into the algorithm. Then, based on the outputs, if it's sorting correctly, you reward the agent. If it's sorting incorrectly, you penalize it. And then you reward it for making the latency as smaller and smaller. But how do we measure latency? This is one of the very difficult problems that we ran into, because the types of algorithms that we were building were sorting small numbers of elements, like sorting 3 elements or 4 or 5 elements, and we had to be able to measure latency on the order of nanoseconds. So what we decided to do was build what we called a latency benchmarking service. So while AlphaDev was playing the game, we had a set of additional machines that were put on the side, and every time AlphaDev generated a new algorithm, or even a partial algorithm, that we wanted to test, we would send it to this benchmarking service. It would then compute the latency tens of thousands of times across multiple different machines. And then using various statistical tests, we were able to generate a single number that reduced significant amounts of noise and allowed us to generate latency on the order of nanoseconds. Basically branching out of all the types of decisions that need to be made. Every time you make a decision of adding an instruction, there are so many more kinds of instructions that could be selected at the next step, and then at the next step, and you have this branching factor. And this makes the assembly game incredibly hard. And the reason for, and if we look at the total number of combinations of algorithms that AlphaDev has to search through, this is on the order of the number of atoms in the universe. And so we need to have a really efficient way of being able to sort through this incredibly large space. So now, AlphaDev, our agent, had 2 key qualities. So firstly, it was built on top of this AlphaZero technology, but we needed to adapt this to the assembly setup. The first thing we did, which you see on this slide, is we had to create a representation that enabled AlphaDev to be able to understand exactly what the structure is of the assembly programs it's building and how these programs affect the dynamics of memory and registers. So this was the first part. The second part was the latency aspect. So we needed to enable it to be able to predict the future latency of a program. So this would mean that you could take on a partial program and then have a prediction of what it thinks the latency is going to be by the time you finish building the program. And this allowed us to compute latency much more efficiently. So with these 2 aspects, we said, well, let's go. Let's start tackling one of these big sorting functions. And there are fundamental sorting functions out there, like, for example, sorting 3 elements or 4 or 5 elements. And what happens is when you call very large sorting functions, like sorting 1,000 elements, it calls these fundamental functions repeatedly. So the hope is that by improving these lower-level, smaller fundamental functions, we can have this effect of improving all sort functions. So we then ran it, and we said, let's see if we can do something with sort 3. It's a really highly optimized function. Is there anything we can discover? And on the left is the sort 3 function that AlphaDev generated from scratch. And what was remarkable for us at the time was that it managed to find an algorithm that was 1 instruction shorter than what currently existed. And we analyzed this for ages, and we were like, there was nothing that you could do to make this faster. But it managed to find something that was 1 instruction shorter. In addition to that, on the right-hand side, we also tackled what's called variable sorting algorithms that could sort up to 4 elements. And this is a function that AlphaDev generated also from scratch. But here what's unique is that it had to do things like branching and determine when it had to switch to a completely different part of the program. And sometimes it hadn't even written that program yet, so it had to understand that it was going to write that program. So there were a lot of these very difficult, complex dynamics that AlphaDev had to try and understand. So we managed to get good results for sort 3, and for sort 5, we managed to reduce it by 3 instructions. And we said, let's try and see whether we can make this available to the world. But to do so, we would have to get these algorithms into an open source C++ standard library where these functions hadn't been updated in over a decade. So we submitted them and went through a process and managed to get it accepted. We managed to get improvements for sorting 5 elements of up to 70%. And we managed to get improvements on over 250,000 elements being sorted of around 2%. In addition to this, we estimate that our functions today are being called trillions of times every day. And there's a corresponding Nature paper that you can check out if you'd like to get more information. So I mentioned earlier, or right at the beginning of the talk, that we wanted to be able to discover faster algorithms, and this is something that we were able to do, but we also want to discover fundamentally different algorithms. Now, if you look here, this is variable sort 4, and on the left-hand side in figure A is what the human benchmark is, or the standard. If you send in, for example, 4 elements, so here the numbers are 8, 6, 7, and 2, the way the algorithm currently works is if it sees that the vector has 4 elements, it calls sort 4 to sort 4 elements. If you send in a vector of 3 elements, it calls sort 3, and similarly for a vector of 2 elements. Now, on the right-hand side is the variable sort algorithm discovered by AlphaDev. And it works in a very different but quite intuitive way, in that given the same 4 elements, it first checks, well, are there 2 elements? And if it was a vector of 2 elements, it would call sort 2, and you were done. But if there were more than 2 elements, in this case there were 4, it immediately calls sort 3. And then it says, well, was it actually a vector of 3 elements? And in this case it's not, but if it was, it would call sort 3, and we were done. And then at the end, it calls a much more simplified algorithm for sorting 4 elements, because already 3 of the elements have been sorted. And it's this aspect of the algorithm that allows us to get significant improvements in both latency and in the length of the program. And so we really think that there is this potential to be able to discover fundamentally different algorithms that can really benefit both researchers and practitioners. So we're now moving on from sorting to hashing to the rest of the computing stack, and Andrea is going to take you through that. So thank you very much, everyone.
Thank you, Dan. So the question now is, can we use AlphaDev to generalize to algorithms beyond sorting? So what we did is we took AlphaDev and we tried it on another fundamental hashing algorithm, hashing. Hashing is an algorithm that was invented more than 70 years ago by Peter Hans-Lu with a very clever idea of bucketizing information to speed up search. So very similar to the image on the top, we often start with a string, we apply what we call a hash function, and that gives a hash. You can think of a hash as a location in a storage. Similar to how a librarian could take a book, and based on the name and the artist and maybe the genre, is going to find the position of the book in the library. That as well is a hashing function. So we decided to try AlphaDev in this algorithm, which is pretty much fundamental in all information retrieval systems, but also, of course, as part of common data structures like hash maps. And we applied exactly on a hash map, which is the one in the Upsale open source library in C++. And we were able to discover a faster hashing function, specifically from 9 to 16 bytes, where we replaced 2 multiplication with a single multiplication and a rotation. And this difference in the algorithm provides similar benefits in terms of quality, but a much speed up in terms of latency, and a reduction of about 30%. I'm happy to say that this was released in the Upsale open source library, so it's now accessible to all C++ out there, of course. And we conservatively estimated that it's being called more than 1 trillion times per day. So if we take a step back, though, we spent a bit of time thinking, where can we use AlphaDev? What type of algorithms can we optimize? And we came up with 2 criteria. The first one is we can either do exhaustive search when we search for the input and outputs. So what do I mean by that? When we discover these algorithms, we need to make sure that they're functionally correct. And there are not many ways to get around that. So for the case of smooth sort, what we are doing is we try the algorithm on every permutations of those numbers. That, of course, doesn't scale. It doesn't scale to large sort, right? So if that condition is not met, for instance, it's not met for hashing, right? We cannot possibly test the hashing algorithm on every string out there. It's not going to scale. If that condition is not met, though, what we can do is, if we don't need the functional the correctness, it's good if we just have a measure of quality. And we have that for hashing. What we do is we take an input distribution of strings, and we measure the quality of the hashing, so things like number of collision or the entropy of the output distribution. And we are lucky, though, that there are quite a lot of algorithms that fit one of these two criteria. Things like JPEG compression, so to compress your images, or things like serialization, like protocol buffer, how do we transfer data across internet, or crypto hashing as well, and so on. But zooming out from algorithms optimization and looking at the entire computing stack, the computing stack is made by many complex layers. And the problem starts much earlier on. It starts at the data center level. There you have a very large number of machines. And a common problem is, how do we schedule workloads and jobs, and which machine do we run? Then after we go from the data centers, there is the problem of transferring the data up to your device in a cost-effective way, but still maintaining the quality, like the problem of video compression. Then, of course, there is the problem of actually running the software and optimizing those algorithms, like we saw for the case of AlphaDev. And finally, the hardware problem. Can we do something to optimize hardware? So starting from resource scheduling, if you look at a particular data center, there you have a very large number of machines. And each machine has different properties, like different values of CPUs, GPUs, RAM. And we need to schedule jobs, and each job has different requirements. So if you want to run a website, for instance, you might need a little bit more CPU. Well, if you're trying to train the next language models, it's GPU the thing you want, right? So all these jobs have different requirements. And it really looks like a game of Tetris, multi-dimensional Tetris. And the problem here is that we want to allocate these resources in a smart way. Because, for instance, if we end up with a machine where we used all the CPUs, but we only have some RAM left, well, the RAM is not going to be used, right? It's wasted. We call it wasted resource. And that is exactly the same in Tetris. In Tetris, if you're left with an empty space and the line doesn't clear, well, it's bad, right? There's nothing you can do at that point. And similarly to Tetris, where planning is very important, it will be very valuable if you can predict what's coming next. And that is exactly what we do in this problem. Oh, so we don't have the slides again. Great. So, yeah, and if you imagine like a resource scheduling similar as a Tetris game, right? So where each job or workload that we're trying to schedule is a piece, what if you could predict what's coming next, right? What if you could tell, okay, maybe like the next job is a job that is going to require quite a lot of CPU? It turns out that we can, because we have access to all history of distribution of workloads, right? So when we train our agent, what we do is we give the history of the workloads of the past, and our agent becomes very good at predicting these patterns and at forecasting. And with that information, is able to leverage it and be able to come up with a smarter scheduling algorithms. And in live testing, so this is coming quite a bit later, so yes, we were here. So in live testing, what we are able to show is that we reduce by about 19% the amount of wasted space. And why is this important? It's important because it means we can do more with the hardware we have, which ultimately leads to a reduction in energy consumption. And taking to a step next, going from data center up to your device, how do we transfer data in a very efficient way, in a way that is cost-effective but still maintain the quality? For instance, the video compression problem. And why is video compression important? It's because nowadays, video streaming takes the majority of internet traffic. And be able to compress this video in an efficient way is fundamental. And there's been quite a lot of work over the years, decades actually, in coming up with efficient codecs like VP9s. So what we did is actually try to apply our agent to a VP9 codec and try to treat it as a game again. Here we're trying to set the quantization parameter. So it's a parameter that tells you the information that you want in each frame. And we treat it as, again, the wrong side, and we treat it as a sequential decision problem. So what does it mean? That we decide the quantization parameter on each single frame. And the intuition here is that not all frames are the same. So imagine you have a frame with an explosion or a car moving. Well, you really care about the information in that frame. But if it's a static image, maybe of a house, well, it doesn't matter as much, so you can probably compress a little bit more. So you can be a little bit clever on how you do these things. But the key idea, though, is that the way you encode a frame is going to affect every future frame. So here comes the planning aspect and the sequential decision processes, where RL, reinforcement learning, is really good at. And in this problem, we were able to save about 4% bit rate while maintaining the same quality. And I'm happy to say that this agent based on Mute Zero is now live on YouTube, powering every YouTube video that you watch. So taking a final step, looking at the last layer, which is the hardware one. Is there anything we can do here? Well, it turns out we can, right? And as well, we treat this as a game. So what we do, we looked at small circuit designs, things like adders, multipliers. These are fundamental components of hardware designs. And putting them together, then it's how you build like larger hardware components. And we treat it as a game with the objective of maintaining the same functional correctness by minimizing the area, or maybe improving the performance, or reducing the latency. As recent as a month ago, we participated in a competition, IWLS, which is the International Workshop of Logic Synthesis, and our agent won the competition, generating a better design for about 83% of the problems. And I think in this space, there is a lot more we can do. So in conclusion, AlphaDev discovered faster sorting and hashing algorithms. Both of them have been deployed to open source libraries, so they're accessible to every C++ developer out there. And we estimated that they're being called about trillions times per day. But taking a step back and looking at the entire computing system, as our society is getting more and more reliant on computing power and on software, it's of paramount importance that we build solutions that can make this digital transition efficient and sustainable. And I strongly believe that artificial intelligence can play a role in that solution. And this is why we're doing this work. And this brings the end of our presentation. It was a real pleasure to be here, and I'll be around if you want to chat, or feel free to reach out by email. Thank you very much.